In this video, we are going to look at some application problems that involve exponents and logarithms. Mostly just exponents, but we sometimes use a log to solve those equations. One of the most common applications is population growth, where this kind of matches those ideas we were looking at with continuous growth for an investment, which we said doesn't happen very often that you get that as a real opportunity. But in population growth, the population is growing all the time. It's not that we have particular points in time that we compound the interest, so to speak. Looking at the variables that are listed here, this value here, which is P naught, we're at P sub 0, P sub 0, or P NAUGHT, which is the same as like 0 or nothing. That's the initial amount that we are starting with in the population. E, of course, is the exponential number. K is the rate of growth, and again, we always have rate of growth as a decimal number. And then time is always in, typically in years. And then P of t is the amount of the population after a given amount of time. We need the growth rate and the units of time to be the same. As I said, it's usually in years, but if they are changed, if it's monthly, let's say, then the time for both would need to be monthly. Here's an example, the population growth of Ghana. In 2013, the population of Ghana was about 25.2 million, and the exponential growth rate was 2.19% per year. So we want to find the exponential growth function using those variables that we had before. So looking at part A, we said P of t is equal to P naught e to the kt. Just go back, and that's the original equation that we were looking at. What have we been given? We know that the original starting population for this is going to be 25.2. We know that the growth is 2.19%, and we change that to a decimal number. So we move the decimal point over 2 places. So that would be 0.0219, and then t is a time that we would plug in. And we want to write that time is the number of years after the year 2013. When we plug 1 in, that'll give us the population in 2014. And when we plug 2 in, that would give us the population for 2015, and so on. So we just want to be clear what the output number is we're getting based on the input number that we give. For part B, it's asking us to estimate the population of 2018. So we're going to let t equal 5. That'll be 5 years after 2013. So we'll plug 5 in for t. And then we'll just plug this into a calculator. Oops, put a 5 there. Plug this into a calculator, and we get about 28.1 million. For part C, it's asking us how long will it be until the population doubles. So if we started with 25.2 million and we multiply that by 2, the new population would be 50.4 million. So I'm going to put 50.4 million here. And we want to figure out what t is, how much time has passed. I know that I want to take the log of both sides because I have an exponential. But before I do that, I want to move everything away from that from that e number. So I'm going to divide both sides by 25.2 here. And an interesting thing happens. You end up getting 2 on the left-hand side. And so, and we'll see this in a couple slides. It turns out that when you're trying to find the doubling time or the tripling time for something, even this is true for investments, that the amount of the original, the principal, or in this case, the initial population, don't matter. The number that we're trying to find, doubling, which would be 2, is what ends up on the left-hand side. And the only thing that really matters is what the rate of change is, in this case, the exponential growth. I'm going to take the log of both sides, the natural log, because I have e in this equation. And so then I have on the right-hand side, the natural log and the e will cancel each other, and I have 0.0219 times t equals natural log of 2. Divide both sides by that decimal number, and then plug into a calculator. So we're getting that t is approximately 31.7 years. And then we had one more question. At this growth rate, when will the population be 40 million? So for part D, we're going to put 40 here. The difference between this problem and the last one was doubling, and so we ended up with a 2 here after we divided. But in this case, we're not going to end up with a nice number, right? We'll divide both sides by that 25.2 because we want to move everything away from the e so that we can take the log. And we don't want to plug this into the calculator until we're done. So what we're going to do is just leave this in a fraction form. So we'll have 40 over 25.2 equals e to the 0.0219 times t. We'll take the natural log of both sides. And this will have the effect of the 0.219t comes down to the front, and when we have natural log of e, this goes away because it's just equal to 1. So that's why I'm saying we just end up with that exponent when you take the natural log of e. And then divide both sides by that decimal number and plug into a calculator. So plugging this into a calculator, we get that t is approximately 21 years. If you'll notice, this formula looks exactly the same as what we were just doing for population growth, and we use this for continuous compounding of money, right? Where P naught would be the original investment, P of t is how much you have after time, K is the interest rate, and t is the amount of time. Suppose that $2,000 is invested at a particular interest rate. We don't know what it is. And it's compounded continuously and grows to 2504.65 after 5 years. We're going to figure out what the interest rate is. So for part A, we know that when t is equal to 0, then we have $2,000. And when t is equal to 5, we have $2,504.65. Okay. So let's look at the formula that we have. P of t equals this. Well, we could say that when t is equal to 5, we could put this number here, 2504.65. Our starting amount is $2,000. K is what we don't know, and we know that the amount of time has been 5 years. So let's divide both sides by 2,000 to move everything away from the exponent. And then we'll take the natural log of both sides. We saw in both of the previous examples that when we take the natural log of both sides, we'll just end up with the exponent. So in the calculator, to get the interest rate, we're going to type in this number, the log of this fraction, and then it will be divided, that whole thing divided by 5. And it turns out that our interest rate ends up being the decimal number that you get is 0.045, which as an answer would be 4.5%. In our equation, we're going to write the decimal version like this, because part B of this problem is asking us to write the growth function. So our interest rate is 4.5%, but our function is going to be P of t equals 2,000 e to the 0.045 times t. For part C, we're going to plug in 10. And this is just a straight calculator problem, right? And you should get approximately $3,136.62. And then part D is asking about the doubling time. We saw in the last example that for doubling time, we don't need to worry about the amount. We're just going to look at the exponential of the interest rate and solve for time. So the natural log of 2 is going to be 0.045 times t. Divide both sides by that decimal, and we get that t is approximately 15.4 years. So this slide is just sort of summing up what we sort of said. We just did this problem here where we said for doubling time, the natural log of 2 is going to be the growth rate multiplied by the time. We don't need to worry about the original amount or the ending amount. We're just looking at the rate of change and the time. So in this example, we're asking, what's the exponential growth rate if the population is doubling every 37 years? So we're going to use this version because we want to know the growth rate. So K is going to be the natural log of 2 divided by the time, 37.7 years. Plugging that into a calculator, we get 0.0184, which is the same as 1.84%. Remember that we always do calculations with decimals and we have to convert them back and forth to percentage numbers. Exponential decay is a similar application where the exponent is negative. When we have an exponent up here that's negative, it's being plugged into the function. Something inside the function is going to be a reflection across the y-axis. And so I can see in these two pictures that in my growth versus my decay function, I've got that reflection happening. All of the ways that we calculate these problems will be the same. It's just that the exponents are negative instead for decay. And when we talk about a half-life, which would be the opposite of the doubling time, we still use these same relationships between the rate of growth and the time. This is used in carbon dating, which is one of the most common applications because over time an object that is found is decaying, right, and it's losing some of its integrity. In this example, we have the radioactive element carbon-14 has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? Well, let's see. If 22.3% of the carbon-14 has decayed, then that means there is still what we have right now, or at the time of this finding, 77.7% remaining, right? (77.7%), if I change that to a decimal, that's going to be 0.777. I'm writing it that way because I don't know how much of this compound I started with, but I know that right now what I'm left with is 77.7% of it. I'm trying to figure out what K is so that I can figure out how much time has passed. Let's do a little work here on the side. Using the relationships I have up here, I know that the half-life is 5,750 years. So can't I say, since I don't know what the rate of decay is, K is equal to the natural log of 2 over, in this case, the time of the half-life. K is equal to natural log of 2 over 5,750 years. And plugging that into a calculator, we get 0.777. 0.00012. That's a really small number. But now I know that I can plug that in here for K. I can put 0.00012 times T. If I divide both sides of this by P naught, the amount of the linen that there was originally, or carbon, the amount of carbon in the linen originally, this is going to cancel, right? And I'll just have 0.777 equals e to the rate times the time. And then I'll take the natural log of both sides, and I'll have the decimal times the time. And then in the calculator, to estimate the time, I'll plug in this fraction. And again, this is telling us approximately how much time was passed at the time that it was found. Plugging in the calculator, we're getting this number. And again, this is in years. It's a pretty long time. All right, so that is our example for half-life. But again, you can see that the process is just the same as it would be for doubling time or any of the other applications. All right, I will see you in class. Have a great day.